Hello, everyone. So, November 2010, Thomas Thwaites, that's a designer from the UK, he gave a TED talk about his project he accomplished before. And this project was called the Toaster Project. His idea was to build a toaster from scratch. So he bought a very cheap toaster from his local appliance store, and he started to disassemble it. And he was quite surprised, or rather dismayed, that this cheap toaster that cost £3.94 was consisting of 404 different parts made of 100 plus materials. So since he had not his entire lifetime, that he does not want to spend his entire lifetime on this project, he focused on 5 core materials. So that was steel, copper, mica, nickel, and plastic. So, and he went on a quest. So he went on a quest for these materials. So he went to a iron mine in north of England, came back with a suitcase of iron ore to extract steel from. He also went trekking to the highland of Scotland in the search for mica. And this entire journey was paved with a lot of failures and setbacks. But after 9 months, he managed to finish his toaster. And the result looked like this. So why am I telling you about this project? Because it reminded me a lot of times about the struggles that we had as a startup from moving from monoliths to microservices when I used to be a CTO of a startup in Hamburg in Germany. So it all started with identifying your candidate for microservice, your bounded context. And yes, it has to maintain the state of its domain model, so it has to access some data storage components. And also has to run on some kind of machine, preferably containerized. It has to provide an API for communication purposes. And it also needs some service discovery there where each service can register to and to be discovered by other services that they connect to. And as soon as you have multiple instances running, you need a load balancer for distributing the traffic and also the workload. And also, since you're communicating over an unreliable, slow network, you have to design for failure and you have to introduce stability patterns, for example, timeout handling, also retries for your failed operations. And this also leads to the characteristics of your microservices that they have to follow idempotency principles, so that repeated operations can result into the same outcome. Also, to preserve your functionality when one service fails is that we have to consider bulkheads, and to avoid cascading failures throughout our entire systems, we have to introduce circuit breakers. Also, for event-driven communication, we have to deal with message brokers as well. And as a single point of entry from the outside, an API gateway have to be involved. Our services are not only consisting of code, but also of configuration, so centralized configuration management has to be considered as well. Yes, it has to be observed, it has to be observable, and so that we can determine its states, its health states itself. And yes, you are uploading also have to consider your Git repo and your CI/CD pipeline for every service. So, and I forgot, backup and recovery, I'm sorry. So, for one service, you have a lot of infrastructural complexities to handle. And if you are a small team with little DevOps practices in place, and you have still to maintain your legacy system, which requires a lot of maintenance and operational effort, and your strategy is to implement new features in a short period of time, you might have to compromise things that should not be compromised. And these compromises might look like something like this. something that took a long time to build, it's very expensive, and in the worst case, even not usable. So for example, this one was just usable for 5 seconds before it blew up because it was missing of installations. So now the question is, how can a small team handle all these infrastructure complexities, but also deliver business value? So since it's very important that we have a business domain focus, because the business domain is that's the one that's generating the visible business value to your customers. And also you have to strategically invest the most of your effort in your core domain, because that's the one that distinguishes you from your competitors. And so the key concept is that you focus on building your core domain that distinguishes you from your competitors and offload all these undifferentiating heavy liftings from your shoulders. So building the core domain and focus on the core domain generates visible business value and also leads to higher customer satisfaction. And offloading the things that are not differentiating you from your competitors is increasing your software delivery performance that delivers your business value faster. So there was a 4 years research run by Nicole Forsgren, Jess Humble and Jean Kim, and they came to the conclusion that software delivery performance has a huge impact on your productivity, on your profitability, and also on your market share. So now the question is, how can we offload this undifferentiating heavy lifting? And one approach is to offload the common building blocks of our infrastructure to public cloud providers. Because the infrastructure, that's the part that's not differentiating us from our competitors. So this brings us to cloud native. So cloud native describes microservices being packaged in containers, being orchestrated by a container orchestration platform that's running on a cloud native infrastructure. And this abstracts away a lot of complexities, infrastructure complexities. For example, your service discovery, your load balancer, your configuration management, also does auto scaling and also recovering, and also provides some aspects of the observability. And you can also use it in combination with additional managed services, so that the burden of managing all these infrastructure complexities will decrease. But, for example, container orchestration platforms such as Kubernetes, it's offloading all your infrastructure complexities, not all of them, but a lot of them. But on the other side, it's also unloading a lot of new primitives that you have to deal with. So this, you have to take care of them as well. And you have to learn them. So this is a really high, steep learning curve in the beginning. And you also have to take care that you not only have to learn all these primitives, but you have to follow some principles as well to become a cloud-native citizen. It's not sufficient just to pack your microservice itself, just to package it in one container and then run it, because it requires to be automated and to be orchestrated by this platform. It requires additional effort, and there are some principles that each container or each application, each service itself has to follow. So one thing is that each container shall address a single concern. So it shall run your service, your microservice, in one single process. If your microservice is requiring additional processes to run, for example, a periodic task, this belongs to another container. And this can then also be orchestrated by Kubernetes, for example, by the cron job primitive. But if a container is addressing a single concern, it's easier for reusability and also replaceability. Another part is that it has to be observable. So it has to provide different APIs for different health checks, and it also has to log important events to standard error and standard out, and has to integrate with tracing and metrics gathering tools as well. It also, so the orchestration platform is providing events for your life cycle as well, for starting and stopping your container. So this gives you the opportunity as the microservice itself to react to these events. For example, catching a sick-term signal to have a clean shutdown process. Also, the orchestration platform itself is providing some events as well. For example, you can also consider of having a warm-up process running before your service itself is fully available. Also, each container image shall be immutable, and that it can be used also and can be used on every environment as well. So every change in your service shall lead to a new container image. And that can be then also shared across every environment without without any rebuild of the container image itself. So this makes it easy to do automatic rollbacks and roll forwards. And each container shall be self-contained. This means all the dependencies that your service is relying on has to be pre-installed during the build time of your container. And for example, your libraries, your runtime environment, your application platform. But except for those configurations or those things that you are depending on that are environment specific. So these are externalized and provided by the environment itself and provided at runtime. Since your containers in the orchestration platform can be replaced by new container instances at any time at any point in time. So this requires that every container has to keep its states externalized. And also, one prerequisite is for short start and shutdown processes that the container image itself is small. And every container requires different resources, so like memory, CPU, and also disk usage. And this has to be declared for every container to the platform itself, so that the orchestration platform knows how to best manage your container. And if you stay confined in these resource declarations, then you're less likely, as your service, you're less likely to be terminated due to resource starvation. So. After we have become a beautiful, wonderful cloud native citizen, sorry about that. So another thing is, what can we optimize as well? So there's another thing that we can optimize, and that's the optimization for operability. And in terms of like handling the application networking reliability concerns, such as service discovery, load balancers, circuit breakers, and so on. So normally you have for example, we already talked about it, the Netflix OSS. That's a client library that every service is referencing to cover these reliability concerns. But this is part of your domain model. So because these client libraries are used there. And optimization is to move these application networking reliability concerns out of your domain model, because and to move the pollution of infrastructure concerns out of your domain, and to move it to service mesh. So service mesh is distributed, decentralized infrastructure that between your services that makes your service-to-service communication safe and reliable. And so the application networking concerns are now moving from your domain model into a sidecar proxy. Every service itself is then equipped with a sidecar proxy, and they are communicating with each other. But also service meshes comes with new primitives that you have to deal with, and it's also increasing our cognitive load. So, and another approach to handle infrastructure complexities is abstracting away a higher part of your infrastructure by following the serverless approach, where all your infrastructure is fully managed by public cloud providers. And the work of the unit of work itself it's shifting from the container to a function itself. So what are the characteristics? So in serverless, we have a fully managed infrastructure by our cloud providers and are working with short-lived functions that are triggered by events. And they can be scaled, automatically scaled with its usage. And you only have to pay per execution. That means if your function is idling, it shuts down and it costs nothing. So how is this related then to microservices? So how can I transform, for example, my microservice into a serverless approach? And you can, for example, in your domain model where you are dealing with aggregates that is kind of like a single unit itself, composed of different domain objects. You can split this aggregate itself in separate functions, and this one per endpoint in action. So for example, if you have the customer aggregate, you can split it in separate functions, and each one is taking care of listing customers or reading customers, creating a new one, updating one, deleting one. And this gives you the opportunity that these functions can run independently and can be scaled up and scaled down according to its usage. An example is, for example, this image processing, where the serverless functions or the functions itself, they are working as a glue between your services and they create a kind of pipeline. For example, you're uploading a document to, in this case, Amazon S3, and this triggers the function that creates a thumbnail. This thumbnail is going to be stored in S3 again, and this triggers another function that updates, for example, the metadata of this image in a database, also updates a search service, and sends a notification, triggers a notification. Which this one also will be consumed by another function that writes a log entry into our log service itself. So it allows large applications to small applications. It allows to be used as automated or automatically scalable backend APIs, and it could be so that you can also cover like kind of peak load and occasional workload itself, but also can, for example, do also for prototyping. For if you start as a startup, for example, and you would like to prototype, it's an easy approach to do so. But also, serverless as well comes also with new primitives, depending on which cloud provider you're running this one, that you have to deal with. And so the thing is that abstracting away infrastructure concerns is good on the one side, but it brings back new primitives that you have to deal with. And this also increases then the cognitive load that you have to overcome with. So, but in the end, it shall deliver opportunities, shifting away your infrastructure complexities to someone else to reduce the total cost of ownership, so that you can build things that differentiate you from your competitors. that you can focus on your core domain to deliver business value, and offloading this undifferentiating heavy lifting in your infrastructure to cloud providers helps you then to increase your software delivery performance to deliver the business value faster. So that we can, in the end, build the toaster on the left side and not the one on the right side. Thank you.